Alright, so when we talk about equilibrium, free body diagrams, force systems, hopefully that's statics. In statics, things are in equilibrium. Okay, so the whole idea of equilibrium is, if it's at rest, it stays at rest. Or if it's in motion, it maintains a constant speed. Okay, actually maintains a constant velocity. The idea is it doesn't deform. Oh, I don't know what that was for. It doesn't deform, rotate, speed up, slow down, any of that kind of stuff, okay? So when we're talking about things being in equilibrium, we literally mean that there's absolutely nothing interesting going on with it. And when we talk about things being in equilibrium, we mean that the sum of the forces is zero, and actually the sum of the moments is zero. But we're going to focus first on the sum of the forces being equal to zero. Now, in order to apply this knowledge, the first thing you have to be able to do is to draw a free body diagram. Okay. Or we call it an FBD. Kind of sounds like something you don't want to get from someone. An FBD. Hopefully this is a reminder of what you did in physics. First of all, if I have a little particle that has some kind of a mass floating in space, remember that anytime you draw a free body diagram for a particle that has some kind of weight, then that means that its weight is mg. So it's mass times the acceleration due to gravity. Now, since most of the problems you're doing are on Earth, your g is going to be 9.1 meters per second squared if you're using metric. If you're using the what you call foot-pound second FPS units, it's 32.2 feet per second squared. Now, what you want to avoid is if you've got, say, the mass is 10 kilograms. So you could go ahead and say, okay, so that means my force is mg. Actually, I'm going to do my forces in red. And I know you don't care, but I really do, because I'm going to use blue for moments later. So that means that the force by this is 10, it's 9.81. So 98.1 newtons. Now, please be careful that later on, if you get a particle in space and they say this is 10 pounds, 10 pounds. When you draw the force is, I should say this is in the negative j-hat direction, but anyway, the force here is, you know what, I'm just going to get rid of that and then that's easier. It's not a vector, I'll pull that. But this force here is 10 pounds, okay? The force is not 10g or 10 times 32.2. It's not that, because remember, pounds is already a force. It's already written in terms of force, so it's already a force. Don't multiply by anything. It's completely content being who it is. Okay? Alright. So, moving on. Something else you need to make sure you know how to do is to deal with springs. So, I'm going to draw a spring that's stretched and a spring that's smushed. So I'm going to call this kind of neutral. So this spring is unstretched. And we'll say that all of these springs have a spring constant of K. Okay? So we got a little mass here, and a little mass here, and a little mass here. The force on the mass caused by this spring here in this unstretched length, so this one's unstretched, and this was extended, and this one's compressed. The force exerted on the particle by this one is going to be nothing. The spring is completely content. Sometimes I get the question, do I consider this whole thing a spring? And the answer is yes. Consider this whole thing as a spring. We're just simplifying it. So whenever this is stretched, this whole thing is a spring. It's just harder to draw, or this whole thing is a spring, so don't think, wow, oh, this is partially a spring and partially wire. No, the whole thing's a spring. We're just simplifying it for symbols and stuff. Okay, so hopefully you recall that if I'm extended S past my neutral state, past my unstretched state, then the force caused by the spring on the mass is going to be the spring constant times the amount that we're stretched. Okay. You got to think, how is the spring pulling on the mass? Let's say, okay, the spring is trying to compress, so it's actually pulling the mass toward its neutral. So, pulling toward neutral. Okay. Now I know some other classes use X or whatever, but I'm teaching out of Hibbler, and Hibbler uses S, so we're going with S. And that's because X is the coordinate axis, so I totally understand. But now if we're pulling S here, think about what the mass is, or what the force is. Again, the force is the spring constant times the amount of compression or extension. But in this case, we're trying to force it to neutral. So the force in this case would actually be pushing down. The force of the spring in particular would be pointing down. So again, we are pushing toward neutral. Pushing towards neutral. Got it? Okay. And the next thing you need to worry about are cables and pulleys. And the most important thing to remember about cables and pulleys, especially in statics when you're just getting started, we have a few assumptions. Come on. And our assumptions include things like the rope or the pull, the cable has no weight. And to solve for a cable with weight, you basically need calculus, and we're not quite doing that yet, but we will eventually, I swear. The cable can't stretch. It's inextensible. That's a favorite word. Inextensible. So the cable is inextensible. We assume the cable has a constant tension throughout its length. And of course the cable's not moving because we're in statics, so it's not moving. That's not really assumption, that's just part of what goes with being in this particular subject area. Alright, so, I don't know what that was. So if I'm looking at a cable, and there's a rope on this cable, or, yeah, a pulley, and there's a cable on the pulley, sorry. A pulley with a cable on the pulley, then the tension in this entire cable is going to be the same thing. Now if I'm pulling on it here, and I'm pulling on it here, I don't know what those are really, but basically that means that the tension here, the magnitude of that tension is going to be the same as the magnitude of that tension. Now obviously the vectors representing those tensions are going to be different because they're pointing in different directions, but their magnitude is going to be the same. Now where this can cause problems, problems isn't the right word, but where this can be funner is, and this will come up, say you've got a problem, like, I don't know, it goes like this, and the rope comes down, and the rope's attached to some kind of a brick, and I don't know, for some reason, I don't have any idea how this would work in real life, but the brick is attached to a pulley that goes like this, and comes up like this. Okay. Now, the cable in each one of these, the tensions, the tensions in each one of these cables is going to be the same within that cable. So this cable would have a tension of T1 throughout it, but this cable over here, would have a tension of T2. So as long as you, and I would do this all the time, and then if I added another cable here, you know, I don't know why that's a really silly cable. But if I added that really silly cable, its tension would be tension 3. Okay, so if I was drawing a free body diagram of the block, whoa, I would not want that to happen. If I was drawing a free body diagram of the block, which I'm apparently incapable of coloring in, no? Alright, this is just getting silly. Okay. Then I can say, okay, well this guy is pulling down with a tension of T1. I don't really know what this guy's doing, so that's just weird. And this guy's pulling up, say, with a tension of T2. Okay. And then, of course, the mass itself has a weight of some kind of mg. Okay. So that's kind of what we're looking at in drawing these free body diagrams. It's just seeing everything that touches, and figuring out how to do it. So let's kind of talk about free body diagrams then. So to draw, we use a free body diagram. Basically, you want to isolate your particle from its surroundings, but it doesn't have to be a particle. It could be your, I hate to say closed system because that just sounds more complicated than it is, you know. But the idea is that if, you know, I've got some forces coming in here and here and here and here, and then it goes from here to 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 here. I don't know what this guy's doing. Here. Rather than looking at this particle, and then this particle, and then this particle, and then this particle, and then this particle, rather than doing all that, I could say, I'm going to pretend this is a particle. And I'm just going to evaluate those 5 forces coming out. And we can do that because in statics, this is okay. Because in statics, we assume that there's no deformation. And by that, you know, by the fact that there's no deformation, I mean that the sum of the internal forces is 0. And this is kind of hinting at what we're going to do later. But, you know, it's a start. Okay? The next step is to sketch all the forces on the particle. So, and again, particle or system, closed system. And it's really important to say not to miss anything. And that's kind of like, duh, but no, for real, don't miss anything. So make sure that you've got the weight of the particle, because sometimes that's something that we miss. And again, make sure you've got the weight in terms of force. So if it's already in pounds, don't multiply it. If it's in kilograms, be sure to multiply it to get it into newtons. Then you want to identify all known and unknown forces. So the known forces you're going to do numerically, right? Because you'll have actual numbers, so you'll have something like, blah, something like that. And unknown forces you need to do algebraically. So don't be afraid to go introduce algebraically. Don't be afraid to introduce something. So if you know, say you know its magnitude, but you don't know its direction, don't be afraid to go in and say, okay, so it's, 300, times some cosine alpha, I hat, or 300 cosine, try this again, whatever, k hat, whatever you need to make it work. This example, or if you know the unit vector, say 1/3, 2/3, and 2/3. So if you know a unit vector, but you don't know the actual force, then you could say, well, the force is going to be the force, times the unit vector, which is why we find the unit vector to begin with. But don't be afraid to go and introduce variables, because you can figure it out later. Okay. Now, when you're actually going to solve these things, to solve in statics, because remember, everything doesn't move, so to solve in statics, you're going to sum all the known forces and set that to 0. Okay? So that's really important distinction. I was going to say, and set resultant to 0. So if I've established that on my particle, I've got, I'm just going to use some things that I make up, and say one of them is this, and another one is, go ahead and line them up. And then we've got some kind of, maybe here's a weight, so it's just, negative 15 k hat. I want to add these all together, and whenever I add, so my resultant, in this case, is going to be this. I guess I should have left some variables in there. Oops. Choice again. This is what I get for not paying attention. Just call this, X, and we'll call this one up here. Silly me. We'll call this one some, P. Like that. There we go. Alright, now I know I want my resultant to be 0, so it's going to be 3 plus X I hat plus 0 J hat plus P minus 12 K hat. But I know that I want each of these to equal 0, right? So that means that 3 plus X needs to equal 0. And P minus 12 needs to equal 0. So I can use this to find my unknowns. Now, it's really important to understand the distinction that I want to sum everything and make sure the resultant is 0. What I don't want you to do is to look at this and say, oh, so X needs to be negative 3. Or, oh, so I can see that P needs to be 12. Don't do this, because when you get to dynamics, you're not summing to 0 anymore. And when you get to dynamics, being in the habit of calculating this like this becomes very, very, very important. So go ahead for success in dynamics, which granted you're probably not going to be in for a while. Get in the habit of actually writing out the resultant, because eventually you're going to be in a position where you really need to know it. Now here I have something that's a negative 3, and that can throw students every once in a while, because you think, well, negative, does that mean it's pointing down? No. Let me give you an example of a nice little particle with a happy little free body diagram. Okay, come here, particle. Particle! Okay, so I'm going to label some forces. Let's just pretend I know these for some arbitrary reason. Okay, and I'll call these F1, F2, this one's 10 newtons, and this one's 5 newtons. Okay. So if I'm going to write these out, alright, F1, I don't know what it is, but it goes to the right. So it has, if I'm just doing IJ, I hat, J hat. So it has, its total magnitude is in the I hat direction. Alright. F2, its total magnitude is in the J direction. So 0 minus F2, and it's in the negative J direction. Let's go ahead and call this one F3 and F4. So F3 is in the negative I hat direction, so minus 10 I hat plus 0J. And F4 is entirely in the negative J hat direction, so 0 I hat minus 5J. Okay. Now, if I go ahead and I add these together, I'm going to get a resultant force of, let's see, F1 minus 10 and minus f2 minus 5. Now I know that I want each of these to be 0, so that means that f1 minus 10 is 0, or f1 equals 10, and then minus f2 minus 5 is 0, so f2 equals minus 5. Okay, here's what's important to notice. This is minus 5. This doesn't mean f2 points down. What it means is your arrow is in the wrong direction. Right? So if f2 equals negative 5, that just means quite literally, my f2 is going down and it should be going up. Now if you just glance at this, you can say, yeah, clearly, because if this is going to be in equilibrium, then if one guy's pulling down, the other guy needs to be pulling up. Well, whoever drew this picture, well, me, didn't apparently know this. And so I drew my arrow going the wrong direction, so that means it's negative 5 down. So the idea is negative 5 down is the same as plus 5 up. Okay? I'm going to also tell you, don't redraw your arrows. If this happens, just go ahead and get in the habit of dealing with those negative numbers, because eventually you're going to run into the same problem in circuits where you're going to say, oh, the current's going this way, and it turns out it goes this way, so you get negative values for current. And what happens is if this is a more complicated system, you're going to be using this force in multiple kinds of equations. And so if you go and you change the direction of the arrow in one equation, you'll have to go change the direction of the arrow in all the equations. So it's much, much better just to leave it as negative 5 and deal with it and move on. So again, just because you get a negative number doesn't mean that it's going down or that it's going left. It just means that it's going in the opposite direction from the direction that you drew your arrow.